No, it's fine. All right, so here we've got sample exercise 12, and we've got our equations that we had written down from the last time we were together. So we're just really going back through this to make sure that we understand what we have done so far. So we wrote our Ka expression for the first reaction because we talked about that the first reaction is going to be in charge of the pH, okay? Now, I have a feeling that when we last left that we did not put this minus X on here. Am I correct or incorrect? We didn't.
You just put it on there to show it.
I think I just put it in there to show you. So can we neglect that X?
Yes.
Yes, we are at least 1,000 times different. So I'm just going to go ahead and, since I wrote in pen, I can't erase it. So I'm just going to scribble that part out. And so we plugged that in and we solved for X. And last time we were together, we found that X was 0.1857. And then we took the negative log of that and we found the pH was 0.73. Okay.
Yes, the X, the H plus.
The X is your H plus. That's right. It's actually two things, Tyler. It's H plus and H2PO4. So we have found the concentration of this, and I think I actually had written it underneath there, 0.1857 is the concentration of that one, and we found the pH. Now, one thing that I need to make sure, oh, I know why we did that. Whenever we find the equilibrium concentration of this one, it is not 5. 5 was your initial concentration, okay? So your equilibrium concentration would be 5 minus X for equilibrium. So, right. So we put in what we know is X, and then when we subtract that, we got 4.81. We did that last time, okay? All right, so we know the concentration of H3PO4, we know the concentration of H2PO4 minus, and now our job is to find the concentration of each one of these. All right, so now let's work with the next ionization, and so we need a Ka expression for that. So Ka is equal to, I'm just going to go ahead and plug in numbers, 6.2 times 10 to the negative 8 equals, on top, we would have H plus, right? Do we not already know H plus?
Yes, you do.
It's X, that's right. So let's go ahead and plug that in. It's 0.1857. And we don't know this value. So, because I don't want to call everything X, let's call that one a Y. All right. And then on the bottom, we would put the H2PO4 negative. Don't we know that value? It is also 0.1857. Oh, isn't that convenient? Look at what's going to happen here. They're going to cancel out, and the value that we don't know is actually equal to the Ka2. All right, so are you cool with how we got this number? No. Okay, so
Or how do we get that as the denominator?
As the denominator, so look at what your denominator was going to be. It's going to be the H2PO4 negative. And didn't that come from the previous equation?
Yes. So,
Yeah, and so those two numbers were actually the same number, okay? Do you need me to push this up a little bit, Caleb? Yes, I'm sorry. Let me move my big fat head out of the way. Here, there we go. All right. So now we have the value of this one, which happens to be 6.2 times 10 to the negative 8 molarity. All right. Okay, and then our last one is we're trying to find the concentration of the PO4 3 minus. So again, let's set up a Ka expression for that one. We have 4.8 times 10 to the negative 13th is equal to, on top, we know H plus. We have that from the first ionization. So that would be 0.1857. We don't know the PO4 3 minus. So instead of us calling that an X or a Y, let's call that one Z. So we don't.
where did we get, I mean, are we doing Ka3 or
Yes.
Ka2?
Now we're doing KA3 because we found,
H, my bad.
yeah, that's our H, and this is a Z. All right, and then on the bottom, our value for HPO42 minus, we just found, didn't we? It's 6.2 times 10 to the negative 8, so plug it in. And we're going to solve for our last one, which is Z.
So we multiply that.
We're going to multiply across your equal sign, and then you're going to divide by 0.1857, I believe.
Well, you put 0.1857 on the top.
Okay, so when you multiply across your equal sign right here, then you've got,
That's what I was.
right, so you've got this times this, which would then be equal to 0.1857 times Z, right? Let's kind of work this out. Okay, so what do you get when you multiply 4.8 times 10 to the negative 13? 2.976. I'm just going to call that an 8 times 10 to the negative 20. And that's equal to 0.1857 Z. Okay, so now algebraically we're going to divide by 0.1857.
That's how I worked these when we didn't have pH, we had to find it with KA. Right, that's the same thing you do.
Similar, yeah.
Well, I mean,
Yes.
you have to-
Yeah.
The end result, that right there.
Yes. How are we doing over there, guys? Are we doing okay? Y'all okay with that? And so what is your final answer for this last one? Whoa, my hand got really big. Okay, so 1.6 times 10 to the negative 19. We worked this one yesterday in sixth period because I think we had gotten a little bit farther. No, we finished this one up, and somebody said, so basically we don't have any of that in solution. Look at how tiny that number is compared to the rest of them. So the one that you have the most of in solution is the H3PO4. Its concentration is 4.81. Then we have this species in solution, which would be the same as our hydrogen ion concentration, right? Then your next species would be this one. Look how much different this one is to the other two. So if you had to rank these, and I can see this as being a little question, which one of these would you have would be the major species in solution? H3PO4. It's always going to be the strongest of the weak acids. It's going to be your major species in solution. Okay? That's bigger than your hydrogen ion concentration. It's going to be bigger than its conjugate base, and it's definitely bigger than the rest of these. Okay? So if you want to jot that down, you may want to jot that down to the side. If the question asks you, in a polyprotic acid situation, which species is going to be greatest in solution, it's always going to be the strongest of the weak acids. Oh, I'm sorry. What? Here? Okay. I can actually make this smaller a little bit. We'll be in acids and bases probably for the next couple of weeks, and we're going to go to kinetics before we take our mock exam. Yeah, we'll take our mock exam the week after we come back from spring break. So I know. So we're gonna have to get Boogie in on it. All right. Let's go. Let's go ahead and go to the next question. Oh, you want to go to? Okay. It's all good. Okay. Okay, so Cab, gentlemen, I need y'all to like settle down over there. Cab is asked to look at number 18, and I'm gonna have to make this definitely bigger, smaller. Okay. All right, and I think I must have worked out that this is not part, yeah, that's not part of our question. Okay, so you've got a polyprotic acid on number 18. This is number 18 you're asking about, right?
Oh, yeah.
Yeah, that's what you're asking about. Okay, so H3BO3, so you need to break it down if you haven't broken that one down. And so you'll tell me what to write.
H3BO3, thinking we got H
Hydronium.
plus H2BO3 negative.
All right, next one.
H2BO.
I'm done.
You're not
I
done.
don't know.
Hydronium.
You just keep
And
going down.
You just keep going down.
I didn't know.
HBO3.
What's the charge going to be now?
Two negative.
There you go. Now we take that one and we keep breaking it down.
Hydronium.
And so you're finished. Once you get rid of all of your hydrogens, you are finished. Okay? And so they gave you the Ka values for each one of these. So Ka1 is belong to that one. Here's Ka2 and Ka3. Maybe I shouldn't have done that, but anyway, you see all your Kas. So the one that's going to allow us to calculate pH is the first one, right? So set up your first one. You've got what's going to go on top of your expression, right? But you don't know either one of these, right? So it would be x squared and then over 0.35. Okay, so solve for your x on that one. And if you haven't done this problem, do this right now, okay?
If you neglect the X.
We're definitely, and I'm going to tell you, look at the,
Always gonna be minus X on, like that number minus X.
whenever you get ready to find that concentration of this
Why is
at
it like-
equilibrium.
why is it like this? Like, I'm worried because like how I understand
Okay.
why there should be a negative.
Okay, so let's go back. This is a good question, and it's a question that honestly we've been kind of skipping our rice table with these to save a little time, but let's go back and let's reflect on that. Okay, so here we've got initial concentration is 0.35, right? Now before you add that to water, or let's just say the at 0.1 seconds, you just drop that into water. Initially, we would say we have none of these, okay? Our change, though, because you have 0 of either one of those, your change has to be minus x for that one and plus x here. And so at equilibrium, that is 0.35 minus x. This one's x and this one's x. So that's where all that comes from, okay? Now, we neglect x if these two numbers are at least 1,000 times different. And my gosh, they're like 10 to the 9 times different. How much? 10 to the 9. That's a billion, isn't it? Yeah. So I have a feeling when you go back in and you try to plug this in to find the concentration of H3PO3, you're not even going to find that it's going to be probably the same number, 0.35. Okay. So
You mentioned that you neglect X because of it.
you honestly don't have to say that you're neglecting X.
Okay.
Yeah, you don't. You don't. But if you had to find the equilibrium concentration of this, you do need to go back in and plug it into your equilibrium right like there. Okay. Okay. So I'm assuming that we've hopefully gotten an X here real quickly.
Oh.
You guys got, do y'all have your set problem set 2 out right now? Are y'all looking at that? Do y'all have a number for X?
Yeah, the X was 1.37 times 10 to the negative.
Okay. And so when we take the negative log of that to find pH, then our pH is going to be a little bit less than, it's going to be 4 point something, I think. 4.86. How would I know that it's going to be 4 point something? Are we all cool? Everybody good? All right.
It would round to more like 1.4.
Oh, would it? Okay. All right. And so does that change your pH effectively?
Yeah.
What would it change your pH to? Okay.
Hold on. Operator error.
Does it actually say that?
Uh,
Operator error.
4.85.
Okay. So tiny bit, but hey, okay. All right. So we've gotten the pH found. Check that off. And now you have to calculate the concentration of all species. So this is just like what we did before. We have the concentration of H plus, right? It is 1.4 times 10 to the negative fifth. We also know the concentration of H2BO3. It's 1.4 times 10 to the negative fifth. The concentration of your H3BO3, what are you going to get when you take 0.35 and you subtract 1.4 times 10 to the negative fifth? Do that in your calculator right now. Let's see what you get. Because remember that we're looking for the equilibrium value of that species.
0.35.
Exactly. So because look how small this number is compared to your original amount. It didn't make a difference significant figure-wise, did it? So it's still actually 0.35. That doesn't always happen. That's why we do have to subtract x, because we saw in the previous problem that it made a big difference. It was 5 originally and it ended up being 4.81. Okay, so now go ahead, Cap. I just put 0.35 above that one, yeah. All right, so we know this one, we know this one, we don't know this one, and we don't know this one. So we have 2 more species to find. Okay, so we do the second Ka expression. So I'm going to just kind of shortcut this. 1.8 times 10 to the negative 13th equals, on top, we know our H. Right? And on the bottom, let's call this a, well, actually, let's call the next one a Y. But do we know this species, H2BO3 negative? Yeah, it's the same, 1.4 times 10 to the negative fifth. Look at what happened. They cancel out. And so that species, if you notice a pattern here, is always equal to your Ka2. Y'all seeing that? Yeah. All right, so this species is 1.8 times 10 to the negative 13th. Last species, find. So we have 1.6. Is that a 14? That's interesting. The second and the third ionization are almost the same strength. Just look, you've got to the negative 13th and to the negative 14th. All right, usually they go a lot more progressively weaker. Okay, so 1.6 times 10 to the negative 14th equals 1.4 times 10 to the negative fifth. We'll call this one a Z. That's supposed to be a Z. Over. So 1.8 times 10 to the negative 13th. There you go, good. Now you guys are solving for Z.
Sunday.
What does it mean by writing out stepwise Ka?
Do you see where I X'd off this? That's what it's talking about.
Oh, so it's breaking it
Mhm,
down.
just breaking it down. That's all you're asking. That's all it's asking to do. All right, you guys have an answer on that one? Anyone?
2.25 or 2.06. Negative 27.
All right,
You said 20.
22nd. Okay, so here's a question. In any polyprotic acid, what is going to be the major species? The strongest of the weakest. That's right. What is going to be the least species?
The weakest.
The weakest? That would be that one. Is that the least?
Yeah.
That's an acid. What is this? Is that an acid? Does it have an H?
No.
It's the conjugate base, right? It's the conjugate base of the weakest acid. So the least species that's in any of these is going to be that very last ion. Okay? The one that's you got the most stuff is the first piece, and the one that you have the least stuff is the last piece. Everybody got that? Tyler?
So
I know you have a question. Okay. So the one that you have the most of, look at your numbers. 0.35. Which one do you have the least of? The last one. Every single time. That's how it works. Every single time, guys. Okay? The one that you have the most of is your weak acid that you start with. The one that you have the least of is after it completely ionizes all the way down, it's that conjugate base, the last conjugate base that you write. Yeah, the major species is this one, H3BO3. What's the least species? There you go. Okay. Yeah, go ahead and turn that in while we're segueing to sample problem. Actually, we're going to go on down to sample problem 15 today. Yes, ma'am. Absolutely. That's fine. All right. Alex, you got your homework turned in, buddy? You do? Awesome. Huh? All right, we're going back to our lecture guide. Yeah, in there. I want to make sure I give you a grade. Yes, Eli. Say again. If you get it to me by Friday, probably not much at all, okay? If you get it to me by next week, you're definitely going to be losing a little bit more. It looked like the pressure dropped. It does. Yeah, look at the weather outside.
So what does that mean again? I'm gonna ask you.
That's fine.
Is
Let's
it
see if I
about
can.
to rain?
Yep.
Or is it just cloudy?
I don't know if I can show it very well.
Are you still recording?
Yes. But it means that the pressure in the atmosphere dropped. You can see.
Look, I can see N-O.
Oh, yeah. Magnifying.
Tyler.
You saw that, bro, right?
Tyler.
Tyler.
Yeah, it just seems like this was slower.
Yeah, it was. You're exactly right. So the pressure has dropped. On Monday, it was way down here. That nice sunny day we had, it's high pressure. Yeah. Me too. I'm tired of the rain. We're going to skip 13 and 14. So I want you to go on down to exercise 15. Okay, and we're going to start working with bases, pH of bases. Now, bases and acids, I mean, honestly, the equilibrium problems are going to be worked the same way, except that when you find your X, it won't be hydronium, it'll be hydroxide. And so you take the negative log of that, and instead of having pH, you'll have POH, and then you just need to subtract from 14 to get pH. So that's going to be the only difference. Okay, so do you know your strong acids? Let's see. Tyler, name one. Strong acid. What? HCl, he said. All right. Oh, Jamari, you had your hand up. Go. HBr, she says. Caleb. HClO4. Caitlin. H2SO4. Who else had their hand up over there? Cab? We got two more. Alex. HI, the friendly acid. I like to call that one the friendly acid. Yeah, it says hi. All right, and there's one more. It is HNO3. Okay, those are our strong acids. And if you don't know those by Friday, it's going to bite you in the rear. Okay? All right. Now, strong bases, remember, are easy because you find them on the periodic table. They make this cool little B. All right? So we start with LiOH. Then we go to where?
Make a B.
They make a B on the periodic table. So start down group 1. NaOH, KOH, and we stop because that's cesium, like cease, okay? So we're going down, and then we curl back up group 2, the AOH2, remember that's a group 2, and then we go continue, SROH2, and yeah, that one's getting a little bit into the, and actually is probably not as strong. So, but look, curl around, and what magic little letter do you have? If you do it just right. And, or since we're trying to get some things to help us to remember this, okay, it's a beaver base is what I like to think of. Those are your strong bases. That's right. How do I make this better for you? Look. But you have your periodic table, guys. You just go down your periodic table and come back around. It makes a cute little B.
Hey, Q doesn't start with B though.
What? Cute doesn't? No, but base does. Base starts with a B. These are your strong bases. Okay. Now, let's go back through this, guys. Okay. If we know, Cab, get your table on task. If we know that strong bases, or strong acids rather, when you put them in water, they dissociate or ionize 100%. Strong bases do the same thing. So essentially, as soon as you drop some sodium hydroxide into water, you have no more sodium hydroxide. You have sodium ions and hydroxide ions. So every bit of this that you put into water is now in ion form, which means that whatever your concentration was of your sodium hydroxide, it's really not sodium hydroxide. It's really the concentration of sodium ions and hydroxide ions, which the part that we care about for pH is hydroxide. So if I want to know the pH of this species, all I do is take the negative log of 5.0 times 10 to the negative 2 equals, so everybody do that in your calculator real quick. And what are you getting for POH? Because that's what this is. We just found POH.
1.3.
Okay, because we took the negative log of the hydroxide ion concentration, which is giving us POH. Now, to find pH, 14 is equal to pH plus POH. So just simply subtract that number from 14. So your pH is equal to 12.7. Is that in the basic range?
Yes.
Yes, it is. Because remember, bases are going to be above 7. So yeah, it's definitely in the basic range. So strong acid, strong base pH is so easy. All you have to do is take the negative log of the concentration. Pay attention, though, to what, if you're dealing with an acid or a base, because if you're dealing with a base, you have to subtract from 14 after you take the negative log. Okay, let's go to exercise 16. Exercise 16. Okay, so now we've got the pH of weak bases. The first one says calculate the pH for a 15 molar solution of NH3. NH3. They gave you a KB. That's a hint that it's a weak base, even if you didn't have that title up here at the top. Okay? So we've got 15 molar solution. Your first job is to show what is happening with ammonia in water. In bases, it is a very good idea to go ahead and include water as part of the process, because remember, water is getting ripped apart. Caleb, you should be writing this down. Water is going to be getting ripped apart. Weak bases are pretty mean to water. They rip them apart. Okay, so if you wrote water as HOH, the breaking point is like right there. So one of these hydrogens is going to be attracted to that lone pair of electrons on nitrogen, and you end up with NH4 positive because you just stole a hydrogen there, plus what's left over from water, OH negative. Okay, so there is your equation. Now let's write a KB expression for this. Remember, water doesn't ever get written in because it's a pure liquid. So KB is equal to NH4 positive times OH negative over NH3. That's right. That's right. And so
So the water is acting as the acid. And
that's right. That's exactly right. Water acts as the acid. Remember that, what is that called when something can act as either an acid or a base? So amphoteric, very good. So water is always amphoteric. All right, so now let's do some plug and chug. We've got the KB, we've got this value, and then on top, each one of these would be an X, right? And so let's 1.8 times 10 to the negative fifth is equal to X squared over 15. Are those at least 1,000 times different? They are, so we can neglect X. And then our X is not equal to hydronium. It's equal to hydroxide this time. Okay, so I'm going to let you guys solve for your X. One six. Okay, so Alex got 0.016. Do you guys, let's get confirmation. Okay, we agree with that. Now to find pH, let's go ahead and take the negative log of this. But that's not going to give us pH, that's going to give us POH. And so it's a 1 point something, I have a feeling. 1.78. And then to find our pH, subtract from 14.
Well,
12.2.
Okay. Okay. All right. Voila. It's not, is it? The more you do these, the easier they get. Okay. All right. Are we good? Everybody good with that one? Okay, let's go to the next one. Now, we're in trouble land here because they didn't give us a formula. So, okay, fine. I still know that a weak base is going to always react in the same way, right? So I'm just going to say, well, there is a thing on our equation sheet. Let's see what that says for KB. Let me see if I can make this bigger for you guys so y'all can see what I'm talking about here. Oh, zoom. All right, do y'all see KB on there? I don't. It is blurry. It's very blurry. Let's try this again. I'm trying. There it is. A little bit better. Okay, so here's KB. So we don't have an equation. Just use that. That'll work, right? It's still going to be X squared over your concentration is equal to your KB value, isn't it? Yeah, okay. So That's what I'm going to put. I'm going to write, let me go down a little bit here. I'm going to put 4.38 times 10 to the negative fourth is equal to x squared over 1. Remember, though, x is equal to your OH minus. When we take the negative log of that, we'll be finding POH. I'm going to say it's 1 point something for your POH. I'm just going to hedge my bets on that. All right, so go ahead and take the negative log of that and find your POH. And then subtract that from 14 to get your pH. .32. Okay. All right. Okay, so now we're going to move into a problem that says salts as a weak base. So let me fix this. That's probably not what I wanted to do. All right. The interesting thing about salts is they aren't always neutral, okay? So you're like, oh, I just put some salt in water. What kind of salt did you put in water? As chemists, I want you to understand that salts are any ionic compound. We think of salt as sodium chloride, right? It's like typical, but salt is any ionic compound. And a salt can be acidic, basic, or neutral. It depends on what each piece comes from and how it interacts with water, okay? So if I have, say, NaF, now the way that you can determine what the salt is going to be is you look at the different pieces that are in that salt. Now, if Na were made into a base, that would be NaOH, right? Is NaOH one of your strong bases?
Yeah.
Yes, it is. So I'm going to put a little SB underneath that for strong base. If F were made into an acid, we would put an H in front of that, and that would be HF. In fact, they gave you the Ka value for HF for a reason. We'll talk about why. But is HF one of your strong acids? No, it is a weak acid. What do we know about the conjugate of a weak acid? That it's a stronger base than water. Yes, we do know that. It's not actually a strong base, it's just stronger than water. Okay, so that means that it's going to govern the pH. If water were the stronger one, then pH of this solution would be 7. Okay, but this F minus comes from a weak acid, which means that it's a stronger base than water. Now, the cool thing about doing this little exercise that I just showed you here is you can determine what kind of solution that this will be just by looking at which one is the strong base, right? So the solution will be basic. That's not why that it's basic. It's basic because of this piece right here. That conjugate base is a stronger base than water, okay? But just identifying what do these pieces come from can tell you what the solution is going to be. Strong always wins, right? Okay, so, oh, I have SB, strong base. It's going to be a basic solution, okay? So we have this Ka value for a reason because this species, F minus, is going to interact with water. So let's draw an equation for what's going to happen when you put this in water. I'm going to write water as HOH. It's just easier to see. All right, F minus is acting as a conjugate, it's the conjugate base, it's going to rip water apart. So what are you going to get on the other side? HF plus OH minus. Do you see why the pH is actually going to be basic? Because you have some OH minuses dropped off in solution from this F minus interacting with water. Okay? Now, since this is a base, then we actually would need a KB expression. Okay? Because KB is HF OH minus over F minus. There's our KB expression. But they didn't give us a KB value, they gave us a Ka value. That's okay. We can figure out what the KB value is from the Ka. Here's a little piece of information that you need to know. Kw is equal to Ka times Kb. Okay? So if we're assuming that this reaction is taking place at 25 degrees Celsius, because they didn't tell us anything otherwise, then our Kw value is what? 1.0 times 10 to the negative 14th. We don't know Ka, and then, oh, we do know Ka. We don't know Kb. Ka is 7.2 times 10 to the negative 4th, and then times Kb. So, real quickly, solve for the Kb value for this base. Say again? You're just going to divide. Move it over. Like 1.0 times 10 to the negative 14 divided by that. (1.39) times 10 to the negative 11. I just went ahead and stuck that up there in my expression. Okay. All right. So now we have enough pieces to solve for pH at this point. Don't we have the F minus piece? Yes, we do. So we could just plug that in here. What are each one of these things going to be? X, X, and X squared, right? So I'm just going to come over here and I'm going to set up my problem. 1.39 times 10 to the negative 11 is equal to X squared over 0.3. And then when I solve for my X, that is equal to hydroxide. Okay, so you'll have to, when you take the negative log, then you'll have to subtract from 14. But let's go ahead and finish this one out. So your POH is going to be 5 point something. How do I know that? 5.69? What am I looking at to determine that? How can I just estimate what the pH is going to be? The exponent, that's exactly right. I'm looking at this exponent, okay? And if the mantissa, that's what this part of the number is called, is actually bigger than 1, then that's going to be less than 6. So it'll be 1 less than 6. So it'll be 5 point something, okay? It won't ever go down to 4 as long as that is a 6. It'll be between 5 and 6. Take the negative log of that number. Somebody did. I didn't. Okay, so negative log, in fact, we probably need to go ahead and put that in, of 2.04 times 10 to the negative 6. And that gives us that. So then pH is 8.31. That's a 9. Here's our final answer. 8.31 is the pH. Okay. So is there really much difference in what we've been doing to this? No? I mean, you got a little bit of difference. If now we worked actually 3 different kind of problems here. We did the pH of strong bases, we did the pH of weak bases, and then we did the pH of a salt. Okay, so let me look and see if there is one more like that. Let's do one more with the pH of a salt, just so you'll have some good problems to look at. Okay, so if you look at the next exercise, they gave us a KB, but we got to look at the salt that they gave us. Okay, so let's break this salt down. First of all, do you recognize that that's not an acid or a base? It's NH4Cl. Does it have an OH on it? Does it have an H on it in the front? No. So this is a salt, okay? NH4 comes from what species? What's its conjugate? Somebody said it over here. NH3, that's right. And so it comes from a weak base. If you don't know that NH3 is a weak base, please learn that today. NH3 is a weak base. Okay, it's ammonia. You might have some of that in your house. I don't know, as a cleaning supply. All right, now Cl. If Cl were an acid, what kind of acid would it come from? And it's strong acid. So looking at that, this solution will be an acidic solution. There you go. Good job. Okay. But it's not because of the strong part. It's because of this part, the weak part. So that's what we're going to put in water, NH4 positive plus water. And what is it going to do to water? Is it going to rip water apart? No, it's going to give one of its hydrogens to water, isn't it? Yeah. So we have the hydronium ion that forms and NH3. Now, what was this acting as, though? What was NH4 acting as?
Acid.
It was acting as an acid. So do we need the Kb or do we need a Ka? We got to have a Ka. Whatever it's acting as, that's what you need. Okay, they gave us a Kb. Great. That's good. I mean, we can find Ka from that. But this was acting as an acid. So Kw divided by Kb will give us our Ka for that. All right, so 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th is going to give us our Ka. That's just a constant. We're assuming that this is happening at 25 degrees Celsius, so that is the constant for water as long as that's your temperature. Alex, did you pick up one of those sheets from Did you pick up one of those sheets from the pickup table? Would you go grab two? One for me, one for you. All right, so what are y'all getting for your Ka value here? Okay. All right, so what are we going to do next? Thank you. What's our next part of this problem? We know it's going to be an acidic solution. How are we going to find the pH? What are we going to do? Yes, I'm sorry. Let's scoot that over. Are we going to take the negative log of that? No.
No, you put Ka.
Yeah, we got to actually, there you go. So 5.6 times 10 to the negative 10 equals x squared over, there you go. Look at you go, yes. All right, so remember, now this time our x is equal to what? Hydronium or hydroxide? H, good. So we don't have to subtract from 14, do we? Oh. Whenever somebody gets the X value, please feel free to call it out.
Would x be 5.6 times 10 to the negative
11? Yeah, did you take the square root?
7.48 times 10 to the negative 6.
Okay. All right, and then we're going to take the negative log of that. And our pH is going to be 5 point, I'm going to just say 5.2.
5.13.
Oh, man. Okay. No, I'm just guesstimating. Yeah, I'm guesstimating. I'm seeing how close I'm coming. Because the bigger your mantissa becomes, the closer you get to 5.00. That should be a -6. Yes. Okay, we're going to stop on working problems on that part because let's look at your practice you're going to be looking at today. Okay, so we're going to be working problem set 3. Everybody got one? Yes. Do what? Oh, just a quiz on your strong acid, strong bases. Yeah. Quiz on strong acid, strong bases. So make sure you get those in your head. Okay? All right. I'm just going to look and see if there's anything that should cause you grief on this. I'm looking to see if there's anything that should cause you grief on this. 9 and 10 you feel like are causing you grief?
Number 6.
Huh. Nah. Because remember, you're using that table. You're using a table to help you figure out some stuff. Yeah. And just remember, the stronger the acid, the weaker its conjugate. Doesn't NO3 come from a strong acid? Yes, it does. So it's going to that's going to be extremely weak conjugate. That means that this one would be the stronger one in that situation.
So NH3 would be stronger.
Because NO3 negative comes from a strong acid. Okay. So I'm going to but you got a table that you can look at. Do you? You can find one in your textbook. There's a table of weak bases in your textbook. Okay, and then let's see what else we got. I don't think you can do number 5. No problem. Oh, number 4. Y'all look at number 4 real quick.
We gotta do that backwards, right?
It does look like you have to do that one backwards. Calculate the concentration that has a pH of that. Let's do that one together. Because it's got 2 OHs. That's a little tricky. I would agree, Alex. So Alex says we should start by subtracting the pH from 14. That'll give us POH, right? And so POH would be, okay, 3.50. Now, what are we going to do from there? We need OH minus. How are we going to get that?
Log. No.
Not the
Anti-log.
anti-log. There you go. So second log. And then we have to make sure we put in a negative 3.5. Second log. Okay, so that'll give you 3.16 times 10 to the negative 4th. Okay, now that's the concentration of OH minus, right? But the question is the concentration of this. You would multiply that. Well, actually, would you multiply that by 2? There are 2 OHs, right? So for every one of these that breaks off, there's 2 OHs. You know your concentration of OH. Would you multiply by 2? You know this concentration.
Wait, what do you divide
That would be just the concentration of 1.
This is the concentration for all of your hydroxide.
Would you divide it by 2?
I think I agree with Alex. Because look, if you let's just write an equation. I want you to look at this. Okay? If you actually this is a one-way arrow because that's a strong base. So you'd have strontium plus 2 OHs. What's the ratio of OH to strontium hydroxide? It's a 1 to 2. So if you know your hydroxide ion concentration, your strontium hydroxide ion concentration, or your strontium hydroxide concentration would be 1/2 of that. So yes, you would divide that by 2. 1.6 times 10 to the -4th. Okay, there you go. Are y'all cool with that concept of,
Why do we divide by 2?
look at your ratio of hydroxide to strontium hydroxide.
It's 1/2.
It's 1/2 of it, right? If we know our strontium hydroxide ion concentration, then we're trying to find strontium hydroxide. Did I just say that wrong? If we know our hydroxide, the strontium hydroxide is 1/2 of that. Okay?
Since the same number would be the same amount of strontium hydroxide as strontium.
Yes, yes,
So that'd be the same concentration.
yes.
And the concentration of strontium hydroxide would be half the hydroxide because it's 2 hydroxide.
That's exactly right. You got that. Okay, now I heard the gentleman over here, Sawyer and Wyatt, y'all said what? Number 9. Let's look at number 9. All right, so codeine is a derivative of morphine. That's interesting. Did you know your cough medicine was a derivative of morphine? That's what's in cough medicine. It was once commonly used in cough syrups, but now you can only get codeine by prescription because of its addictive properties. Interesting. If the pH of a 1.7 times 10 to the -3rd molarity solution of codeine is 9.59, calculate Kb. So codeine is acting as a, look at that species there. It's got a nitrogen in it. When you see something that's got a nitrogen in it, that's got a lone pair of electrons on that nitrogen, which will cause that to act as a base. Okay? So that's why they want us to calculate Kb. All right, so we know the solution, the concentration of this, the base is this. We know the pH is this. We need to do a little bit of backwards work here. So instead of us needing pH, we need, because it's acting as a base, we need POH. So what's the POH?
Okay, what's the
Would be something.
rest of it? So
1.7.
see, this is a little confusing. I'm forgetting.
13.999.
Would we do 1.1 times to the -14 divided by that?
By the what? The concentration?
The pH.
No. So we just need to find the POH.
How would you-
You just subtract from 14. So 14 minus 9.59 is going to give you,
That's 4.41.
oh, Alex. Okay, 4.41. Now we need to take the anti-log of that to get us OH minus. Second log. Remember, put in negative 4.41.
Right.
So 3.89 times 10 to the -5th. But I'm going to let you guys remember it, because you have to get rid of the negative part of that equation. You do have to put a negative 4.41 in there. So this is 3.89 times 10 to the -5th.
14.
Okay. If your species is acting as a base, so you've got this base. I really don't want to write it out, but I will. Okay, C18. I know I'm getting a little lazy, aren't I? 21NO3 plus water. Okay, and so it's going to rip water apart, right? And so one of the H's is going to come up and buddy up over here. So you'll have HC18H21NO3. positive. Good, Alex. Good catch. Plus OH minus. Okay?
That's a lot, yeah.
That's just your equation. Now, if you wanted to cheat a little bit on these practice problems, hey, I would do, I mean, you know you're going to plug it into this KB kind of thing. So it'll be OH on the top plus your conjugate divided by your base. Okay? You could if you wanted to. So this would normally be an X, and this would normally be an X, but don't we know this value?
Yes.
So that means we also know this value.
Oh,
Yeah. And we have the original concentration of this. So our job is to calculate KB. So KB is equal to 3.89 times 10 to the negative fifth squared over your original concentration. 1.7 times 10 to the negative third. Quick question. Ooh, this is scaring me. Why is it doing that weird stuff?
it's been doing it.
Oh, I don't like that. That may mean my dongle is going out. That's what that's called, to connect. That
Call it something else.
that is what it's called. I agree. What do you want to call it? Connectivity piece from the MacBook to the blue cord. Adapter. That. All right, guys. Hey, before we do this, let's talk about this real quick. Would we not need to subtract X for that bottom number? Because we're trying to find the equilibrium constant. So this bottom number needs to be minus, that number minus 3.89 times 10 to the negative fifth. It might not make a difference significant figure-wise, but we need to see. So I want one of you to calculate it without subtracting. Who's got it? Who's going to? All right. Calculate it without subtracting. The rest of us are going to calculate it with subtracting, and we're going to see if it makes a difference in what we write down as our answer, because we actually will need two significant figures in our answer. So you did both. What do you have for without subtracting? Without subtracting. Okay, and so the rest of us, we're trying to see what we're getting.
Oh, no, there.
That's what you got without doing the subtraction part on the bottom. The rest of us are going to subtract. It does make a difference. So 9.1 times 10 to the negative 7. I will tell you guys, last year, well, you said not really, which meant that there is a little, you got an error? All right. I got to see my numbers here.
I'm not getting an error, but
I always
I
get
know I'm not
errors when I type it wrong and stuff like that.
Oh, forgetting to square it. Come on.
Yeah. 9.1 times 10 to the negative 7. Okay, let me tell y'all a little story. From last year, they had a question that was actually like this one on the AP exam. And the students that did not subtract their X on calculating their KB missed a point. When you only have a 10-point question, you try to get as many points as you can, okay? Because missing a point takes you from 100 down to a 90. But if you already missed it, yeah, like real quick. So you want to try to get as many points as you can as you're going through this, because 1 point could be the difference between a 2 and a 3 sometimes, okay? So Your goal is to learn and study. If you're not studying on your own time and doing your own practice problems and doing the struggle through this, you're going to suffer on your test, I will tell you. Which one? But on your own time, like struggle, make yourself go through it, and you got to do the work. Got to put the work in. It's just like anything else. You got to put the work in. Okay. When you get stronger at something, got to put the work in. It does, but when you get through that hole in the wall, you'll be stronger on the other side. Okay.
Your hands gonna hurt.
Gotcha. Do you are you cool on this problem right here? Are you fine? Somewhat. Did you see how I've tried to put my calculator up there so you could see?
I just squared it first.
Okay.
But once you get the answer,
Yeah. Yeah. Now, did you put that bottom number in parentheses? And you just do that. Now, are you using E and not times 10, right? Just E. Okay. Are you using your annotate button down here at the bottom of the calculator for your negative sign? This button? Yes. Okay. I'm just kind of checking. So just try putting it in there again, Javante. All right, guys. Jenna, click our lights on. And don't quit. You guys have 10 minutes to help each other out. So,
Can I go use the restroom?
yeah, I would get my strong basis calculations done. Aren't they strong bases?
Okay, so for this one, when would I have to subtract, subtract that number down here?
Okay, so your job is to do what?
I'm
You
looking
have
for
the KB.
I'm looking for the
Oh, you're determining the initial concentration. Since
So
it's
I backtrack,
initial,
and I got my OH, and I got the top part of the X, and I have my KB. So do I need to subtract this
No.
number? No?
because it's initial, they're asking you for initial.
So I don't have to.
No,
Okay,
no.
I was worried if I had to subtract.
No, and so that's the difference in what you're doing. If they ask you for equilibrium, yes, subtract. If it's initial, no, subtract. Okay. Okay. Hey, yes, sir.
April 1st,
Yes.
mock reading.
Yes.
I got y'all the school vehicle
Yay.
because I don't have the money to pay you much.
Okay. Okay.
But we sent it in now, so probably the day before we get the keys.
Okay.
From Bell.
Sounds good. Sounds good. Yes, ma'am.
So these would be the same because they have the same concentration.
Actually, yeah. No, actually they wouldn't because barium hydroxide has 2 hydroxides in it. So you need to multiply that times 2. Hey guys, on number 2, barium hydroxide is BaOH2. So your concentration of OH wouldn't be 0.4, it would be 0.8.
8.
It would be twice as many.
But why do we multiply by 2?
Because sodium, like on number 1, sodium hydroxide is NaOH, right? Okay. Barium hydroxide is BaOH2. You have twice as many hydroxides in there. Okay. So when that breaks apart, you're going to have a 2-to-1 ratio with your original concentration to now your hydroxide ion. You just have to multiply it by 2. And then take the negative log of it because it's a strong base. Okay. All right.
So wait, we take the negative log of
The 0.8 because these are strong.
Oh,
So remember
we
with
don't
this,
need a KB.
yeah, well, you don't need a KB, you don't need a Ka with your strong acids and strong bases. You just plug it in. Yeah. Good, good. And then find your pH from that. What do you need? Go grab a book and I'll show you where they are.
All you did was the negative 1.1. No, just 0.3.
Well, that should be a
Yeah.